Chapter 7, Lesson 3, starts our lesson on similarity and transformations. Previously, we talked about how if we translate, rotate, and or reflect an image that keeps the same size and the same shape, it is called congruent. Now we're going to move into what happens if we add a dilation in there. And a dilation, as we know, either shrinks or enlarges our picture, called enlargement and reduction. And if that were to happen, we're going to have what's called similar polygons or similar figures. For similar, we're going to say that two figures that can be obtained from the first by a sequence of transformations and dilations. So they're the same shape, but different sizes. Now I'm going to add something to what's here. What if we also talked about some notation? If we want to say is similar to, we're going to use just this mark here, which you'll recognize is on our congruent symbol. If you notice, the symbol for congruence is a combination of the equal sign and the sign for similarity. Now that's on purpose. Let's go ahead and take a look at an example of how we can determine whether two shapes are similar or not. So in our first example, it's asking us to determine if the two triangles are similar by using transformations. So we need to first figure out if there is a transformation that will take triangle DEF and put it where triangle GHI is. So let's start there. First, note that these are facing the same direction. So it's not a rotation, it is not a reflection. They are in different spots, so we must have had a translation. And let's talk about where it translated to. I'm going to go with the right angle here, and I'm going to notice that it went down 2 spaces. So translate, we have down 2 spaces and 1, 2, 3, 4, 5 spaces to the right. So let's state that. We'll say translate 5 units right and 2 units down. That covers the first part. Let's go ahead and now figure out whether all the sides have the same ratio. And what I mean by that is we're going to look at how the sides compare to each other. For example, I see that side DF is 3 spaces. So DF, I'm going to set this up as a fraction. That's 3 spaces. And GI, which is the corresponding side to this, is 1, 2, 3, 4, 5, 6 spaces. So for GI, that's 6 spaces. So I'm just setting up a ratio of each side to its corresponding piece. We always want to go ahead and reduce this, and I see that they have a ratio of 1/2. Now I'm hoping that if I check DE and GH, they are also in the ratio of 1/2, but Let's see what happens. So for D, E, and GH, let's fill in their lengths. DE is 1, 2, 3, 4 spaces, while GH is 1, 2, 3, 4, 5, 6, 7, 8 spaces. And 4 over 8 reduces to 1/2. So far, we are good. But there's one problem. We're going to have to go and figure out what the length of those two diagonals are. So I want you to take a moment. I'm looking at two right triangles. And I would pose the question, how do I find the length of the diagonals? The answer to this would be to use the Pythagorean theorem to figure out the missing piece. In this case, we are finding the hypotenuse. We're finding our C, so we could solve the following. We could do 4 squared plus 3 squared equals, I'm going to call it EF squared. Let's see, 4 squared is 16 plus 9 equals EF squared. 16 and 9 is 25. And to finish solving, I need to take the square root of both sides to find that EF is equal to 5 units. So I know that EF is 5. We're going to do this one more time, but with our numbers for GI and GH. This time, we could have 6 squared plus 8 squared equals HI squared. Now, I know there are some teachers who tell you that you want to have the smallest number first, and I realize I broke that when I did 4 before 3. Check it. You should find that you would get the same answer. Let's continue. 6 squared is 36, plus 8 squared is 64, equals HI squared. Next, 36 plus 64 is 100, equals HI squared. And I conclude by finding the square roots. 10 is equal to HI. So I'm going to go back to my ratios and put HI and put 10 here. And we're going to find that it is a ratio of 1/2. So let me highlight this. We found that each corresponding set of sides have equal ratios. That means that these two triangles are similar. So we're going to make the statement that says triangle DEF is similar to triangle GHI. So because we could identify a transformation and found all three ratios to be the same, these two triangles are similar. What I didn't show you is below there were steps to think about. Step 1, find out if a translation, reflection, or rotation has occurred. We determined it was a translation. And after that part is complete, you're going to make ratios to compare the old to the new lengths. And then it also includes the question, how do I find the hypotenuse of a triangle? And that always is Pythagorean theorem. Let's try that again with these two rectangles. First, let's talk about a transformation. Let's take rectangle TUVW and translate, rotate, or reflect it so that it is on WXYZ. Well, one way to do that is we could do a rotation. So rotate. We just need to stand it upright, so that's going to be 90 degrees. And we're going to do that in a clockwise direction. So we know we could have a rotation to make that work. And I'm actually going to put on this graph what that rotation looks like, just to show you. It would be here. So go ahead and take a look at the red and the green rectangles. They appear to be similar. They're the same shapes. They're rectangles. But are they the same? Do they have proportional sizes? Do the sizes of the length and the width have a ratio between the two rectangles? Let's find out. Let's start with TU. And one side it could correspond with is ZY. Well, that is 3 and 4. So it seems like I'm working with a ratio of 3 over 4. I want you to notice that that is the same exact ratio that WV and WX have. If you look, WV has a length of 3, while WX has a length of 4. Let's check out the other sides. Let's look at TW. TW can correspond with WZ. TW has a length of 5, while WZ has a length of 1, 2, 3, 4, 5. So hold on, I lost count. 1, 2, 3, 4, 5, 6, 7. So 5 over 7. That is the same ratio we would have if we did U, B, and XY. Notice that these are not equal ratios. So ratios not equal. Therefore, T U V W, that rectangle, is not similar to W X Y Z. And a way we can write that shorter is we could say the side for similarity, that sign right here, and put a slash through it. Just like when we say things are not equal or not congruent. So that's an example of one where they are similar, one where they are not. Another thing we could do is to use the scale factor. Similar figures have the same shape, but may have different sizes. The sizes of two figures are related to the scale factor of the dilation. And we have this chart. It says if the scale factor of the dilation is between 0 and 1, then the dilated figure is smaller than the original. And we've seen that before. One way we have seen it is to say the following: 0 is less than k is less than 1. K being our scale factor. Next, if the scale factor of the dilation is equal to 1, then the dilated figure is the same size as the original. And the last statement says if the scale factor of the dilation is greater than 1, then the dilated figure is larger than the original. All of this is review. So let's take a look at how we can use it in more of a real-life example. Ken enlarges the photo shown by a scale factor of 2 for his web page. He then enlarges the web page photo by a scale factor of 1/2 to print. If the original photo is 2 inches by 3 inches, what are the dimensions of the print? And then it asks, are the enlarged photos similar to the original? So here's what we're going to do. We have two parts here. The first action that happened was that Ken took the photo, which is 2 inches by 3 inches, and he enlarged it by a scale factor of 2. So we're going to do that. We're going to multiply the dimensions by 2. And I have that when he did that, he now had an image that was 4 by 6 inches. The second thing he did is after he put it on the web page like that, he took the photo one more time and enlarged it by a scale factor of 1.5. So I'm going to take the 4 inches by the 6 inches, and now I'm going to multiply that by 1.5. When I do that, I find the dimensions of 6 inches by 9 inches, and that is the answer for the first part that asks us, what are the dimensions of the print? Then it asks us, are the enlarged photos similar to the original? Yes. they are similar, and the reason being is that when you perform a dilation, we are automatically going to have similar shapes. If we can find that there is one scale factor used to enlarge and reduce the picture, then it is similar. Unlike in example 2, where we found there was not a single scale factor. This concludes this video. If you have any questions, please feel free to ask.